Press play and a track starts. It takes a fraction of a second. Behind that single input is an engineering challenge of massive scale. A global streaming platform must deliver a catalog of over 50 million tracks to more than 500 million active users, while maintaining playback latency under 50 milliseconds. A traditional monolithic application, where a central server receives a request, finds a file, and sends it back, collapses entirely under this volume of traffic. To survive, the architecture must be highly decoupled and distributed across hundreds of distinct microservices. This node graph connects a mobile device to 3 domains. First, the transport layer, edge servers delivering audio with zero buffering. Second, state and telemetry, syncing playback logs and leases upon reconnection. Third, intelligence, a machine learning pipeline processing interactions for personalized playlists. Operating a platform of this size requires moving past general cloud computing principles. We have to look at the exact mechanics of chunked HTTP delivery, offline lease synchronization, and hybrid neural networks. We start at the transport layer, tracking how an audio file physically moves from a data center to your phone. Live video platforms often require custom transport protocols, like UDP or QUIC, designed to tolerate packet loss and prevent stream stalling during live broadcasts. But pre-recorded music streaming solves a different problem. The audio files are entirely static. Because the content never changes in real time, standard TCP over TLS, standard encrypted web traffic, is highly effective. At the origin server, the raw studio masters are heavily compressed into formats like OGG Vorbis and AAC, optimizing them for high fidelity at low bit rates. Those compressed files are not sent as single, massive objects. Instead, the continuous audio is sliced into uniform segments, typically around 512 kilobytes each. To buffer the track, the client application issues an HTTP GET request, but it utilizes specific range headers to ask only for the bytes that make up the next required chunk, for example, bytes 0 through 524,287. These specific range requests rarely make it to the main origin servers. They are intercepted geographically close to the user by Edge Content Delivery Networks, or CDNs, operated by providers like Fastly or Akamai. If the Edge server has that chunk in its cache, it immediately returns an HTTP 206 partial content status, delivering the 512 kilobyte segment directly to the phone. Because popular tracks are requested millions of times a day, they cache perfectly at the edge. A highly requested pop song will hit a near 100% cache hit ratio, meaning the primary databases almost never have to serve the actual audio file. Treating audio as static, chunked HTTP requests allows the system to push the delivery workload to the extreme edge of the network. This protects the origin servers from traffic spikes and drives seek latency down to 0 for the listener. Pushing data to the edge solves network latency, but mobile devices frequently disconnect from the network entirely. To handle this, the architecture shifts rely on the hardware constraints of the user's phone. The client application allocates a dedicated partition in local storage, recommending at least 1 gigabyte, to act as an offline cache. Due to strict digital rights management requirements set by record labels, users cannot simply download standard MP3s. All audio chunks placed into this local partition are encrypted at rest, unreadable by the device's native file explorer. Manual playlist downloading relies on this cache, but the platform also employs an automated mechanism called offline backup. The application continuously monitors your streaming behavior. Without requiring a manual prompt, it silently retains your most recently played tracks inside the encrypted cache. When the operating system detects a loss of network connectivity, the client automatically generates a dynamic playable interface populated entirely by these hidden cached files. This countdown timer dictates the limits of that offline playback. The local files are bound by a strict 30-day lease timer attached to regional licensing agreements and subscription tokens. The client must execute a back-end ping at least once every 30 days. This connection verifies the user's active premium subscription, updates any expired licensing rules, and resets the offline timer. Crucially, this sync forces the device to offload its cached telemetry. Every play, pause, and skip that occurred while offline is packaged and dumped into Apache Kafka, a high-throughput distributed message queue. This telemetry sync is a rigid business requirement. Streaming platforms owe precise payouts to rights holders, making it impossible to discard offline listening history. Offline mode operates as a temporary, encrypted state disconnection. It relies entirely on Kafka to securely synchronize legal and financial telemetry back to the origin, ensuring accurate accounting once the network is restored. That telemetry flowing into Kafka serves a second purpose. From the message queue, interaction events are routed into a NoSQL database, like Cassandra, to construct massive user profiles. This is the raw data used for collaborative filtering. Instead of asking users to explicitly rate songs, the system evaluates implicit signals: how many times a track was played, if it was skipped, or if it was completed. This grid is a sparse matrix. It maps millions of users on one axis against millions of tracks on the other. Because a single user only listens to a tiny fraction of the catalog, the vast majority of this matrix is empty space. To find meaningful patterns in that empty space, the platform applies a mathematical technique called alternating least squares, or ALS. ALS factorizes the sparse grid, converting it into two dense matrices. One represents users, the other represents items. By multiplying these dense matrices together, the algorithm can predict the exact numerical value of the empty spaces, calculating how much a user will like a track they've never heard, based on a shared latent preference space. But ALS has a critical blind spot: the cold start problem. If a brand new track is uploaded today, it has zero user interactions. Without data in the initial matrix, ALS mathematically fails to recommend it. Mathematical behavior analysis effectively maps known data, but it is blind to new content. Recommending a song that no one has heard requires analyzing the actual acoustic properties of the music itself. To solve the cold start problem, the platform runs a secondary, dedicated machine learning pipeline that analyzes raw audio during the ingestion process. When a new audio file arrives, the backend applies a short-time Fourier transform. This operation takes a one-dimensional audio waveform and converts it into a 2D heat map known as a MEL spectrogram, visualizing how audio frequencies change over time. The system then feeds this image into a deep convolutional neural network, the same type of architecture typically used for facial recognition or image classification. By treating the audio as a picture, the neural network scans the visual frequency bands to extract objective acoustic features: tempo, key, and rhythm stability. The final output of this network is a dense numerical vector. It is trained to perfectly match the format of the collaborative filtering matrix, essentially predicting the song's latent item vector without needing a single human to listen to it. By converting raw audio processing into a computer vision problem, the system extracts the acoustic DNA of a brand new track, allowing the recommendation engine to instantly match it to users who prefer that specific sound profile. Zooming out, the scale of the unified architecture becomes clear. The three domains, physical streaming, state management, and algorithmic intelligence, are entirely isolated, yet intricately wired together. The elegance of this system lies in that decoupling. The domains communicate asynchronously through event streaming, ensuring that a failure in one area does not bring down the entire platform. The loop starts when a user requests a chunk. The CDN delivers in. The device logs the interaction, flushing the event through Kafka into Cassandra. ALS and CNN models factorize this data, pushing metadata back to generate tomorrow's personalized playlists. Global scale is achieved through deliberate architectural decoupling, pushing static delivery to the edge, isolating state on the client, and calculating algorithmic intelligence asynchronously.